I'd like to start today by taking questions. So if you have anything from Chapter 4 that you want to talk about, now's your chance. Ryan.
Can you do number 13?
Sure. Okay. So here we're asked to do this without using our calculator, so we're going to need a unit circle to do that. So let me grab one of those real quick. All right. So cosine of, so we're going to work from the inside out. So I'm going to first retrieve the value for cosine of 7 pi over 4. So going to the unit circle, we'll find 7 pi over 4, which is root 2 over 2. So far, so good. Now, the fundamental range for cosine inverse is 0 to 2 pi. So I'm going to look inside of 0 to 2 pi in my unit circle for the place where the x-coordinate is root 2 over 2. So if I go over here, that's the only place. So I'm looking for pi over 4. Yes, that would be something that you'd want to have memorized. So if we go back and we looked at the 1028 notes. Oh, must have done it before that. Oh, no, we didn't. There it is. So sine, cosine, and then tangent. But yes, you definitely need those for several of these types of problems where we're using the unit circle. Zach.
So how'd you get it? I missed the step where you went from cosine is 7 pi over 4 to just what was the first step? How did you eliminate the cosine?
So I went to the unit circle and found the value for cosine of 7 pi over 4. So 7 pi over 4 is here. And on the unit circle, cosine is x. So cosine of 7 pi over 4 is root 2 over 2.
And how did you know that quadrant? Just because that's where cosine is positive?
Well, 7 pi over 4 tells me where to look.
Okay.
Right? So I found the angle on the unit circle and then pulled the coordinate from the angle. So the angle measure is going to tell me where on the unit circle I need to find it. Because there's only one place the coordinate shows up. Or the angle measure shows up. There's lots of places where root 2 over 2 shows up. But if I have the angle measure, I know exactly where to look. Does that make sense?
Yeah, that makes sense.
As opposed to looking for the coordinate, and there's lots of angle measures where that coordinate shows up. Oh my. Eric. Which one?
15.
From the same problem
Yes.
set? Okay. Any follow-ups on this one before we move forward? Emily?
So how did you, I got how you got pi over 4, but is cosine inverse? Is that if you're still looking for the x coordinate,
So, like sine, cosine, etc., take angles and turn them into like a ratio of side lengths or a coordinate on a unit circle or whatever, just a number. Cosine inverse is going to take a ratio or coordinate on the unit circle and take that back to an angle measure. So that's what the difference between those two things is. So what cosine inverse is giving back to me is an angle measure. And I want the angle measure whose x coordinate is that value. So does that, that's what you're kind of asking, right? It's like, what's the difference between cosine and cosine inverse? Okay. Okay. Lexi, is this a question or a follow-up?
It's a question.
Okay, so Eric's, we got one for Eric, and then if you have a follow-up, to this, I can take that now, but if you're next in line after Eric's question. You have a follow-up or no? Okay. So Eric, you said 16? Yeah. Is that right? Okay. So this is a purely calculator question. So really what I'm going to do here, come on. Goodness, come on. So what we have is like theta equals cosecant inverse of negative 1.5, right? That's kind of equivalent to the equation cosecant theta equals negative 1.5, right? So this is what I'm going to be typing into my calculator. I'm going to type in both sides of this equation and find the intersection of them. And I'm going to look for that intersection over that range of x values. So go to my calculator. I'm going to make sure that I'm in radian mode, since this is clearly a range of values that are in radians. So that's good. So I don't have a cosecant button, so I'm going to type in cosecant as 1 over sine. Remember that cosecant is just the reciprocal of sine. And then I'm going to type in negative 1.5 as the other. Then I'm going to go to my window and set the x minimum to be pi over 2. And I'm going to set the x maximum to be 3 pi over 2. And then I'm going to look for the intersection of those two lines. So let's just go ahead and graph. So this first thing coming in is cosecant. And then the straight line is negative 1.5. So the intersection I'm looking for is right around there. So I'll do second trace, pick the intersect command, and then I just press enter 3 times. 387 is my answer. Does that feel okay?
Yeah.
So this was all on the calculator. Lexi, you were next, right?
Yeah.
Follow up to this one before we take Lexi's. Oh my goodness, Edmund.
So Eric's question would be like, use calculator to find value of the inverse of a specific interval. Is that what it would be?
I mean, you could do it that way, I guess, but no, not really what I was thinking. That's more like worksheet 2 is what you're describing.
Oh, okay.
Emily?
So I missed it. Like, what did you?
I did cosecant and then negative 1.5 each side. And in general, if you ever have an equation that you don't know how to solve, like you can solve them graphically by just graphing each side and finding the intersection. Jack?
So is putting any x in the calculator is the same as the theta?
Yeah, just a variable name. Yeah. Okay. Lexi, is it your turn?
Yeah. 22.
Okay. So this is a story problem. It says Manuel's going hiking. He gets the trailhead. It says current elevation is 174 meters. And then the next marker he passes, he's now 210 meters above sea level. And it says that during that leg of his journey, his horizontal distance he traveled was 1 kilometer. I'm going to write that as 1,000 meters just so everything is in the same unit. So this I can see there's a right triangle right here. And that vertical side of the right triangle just must be the difference between 210 and 74. Is that cool? So if I want that angle theta then, I just need the tan inverse of opposite over adjacent. And I'm probably going to do this in degrees, since most of the time if you're talking about angle measures to normal people's, typically we describe those in degrees, right? You wouldn't be like, man, that was a tough hike. There was a 0.47 radian incline. Like, you wouldn't say that to your, it would be kind of meaningless. Oops, I meant 36 over 1,000, not over 100. 19% grade would be crazy. 2.06. Or 19-degree grade, I guess I should say. Yeah, that's a monster, right?
Why do you use tan inverse there?
So relative to the angle theta here, I know about the opposite and the adjacent.
So you can't use just regular, use tan inverse.
Well, regular tangent takes an angle and gives you a ratio of side lengths. I'm looking for an angle, so I need tan inverse, right? So if you're looking for angles, you use the inverses. If you're looking for like a ratio of side lengths or something about side lengths even, you're going to use the non-inverse versions. Is that okay? Is that, Lexi, you good with what to do there?
Yeah.
Okay, sure. Who's next? Amy.
Oh, could you do
Yeah, what page are we looking at? Okay, page 1, letter H, right? Okay. So the first thing I'm going to do for these problems like this, where we're not giving a range for the theta, is I'm going to have to use the fundamental ranges for these inverses. For that, for cosine, it's 0 to pi is the fundamental range for cosine. So all I'm going to do then is I'm going to go to my unit circle and look for where the x-coordinate is negative root 2 over 2 in between 0 and pi. So going to my unit circle, zero's here, pi's over here. The only place where the x-coordinate is negative root 2 over 2 is there. So my answer should just be 3 pi over 4. And that's it. Sure. Natalie?
maybe just do worksheet 4, number 7.
Worksheet 4. Okay. So on these kinds of problems, we always want to work from the inside out. So arc sine of 2x plus 1 is going to give us a value for theta, right? It's going to give us an angle measure, which is equivalent to saying we need a sine theta that's equal to 2x plus 5. So I'm going to draw a right triangle. I'm going to label one of the acute angles theta. And I know that sine is opposite over hypotenuse. So I'm going to label the opposite side 2x plus 1 and the hypotenuse 1.
Isn't it hard for the secant?
Oh, thank you. Thanks. So it should be hypotenuse over opposite. Excuse me. Thank you. So far, so good? Okay, I can use the Pythagorean theorem to solve for this side that I'll call b. So I know that a squared plus b squared is equal to c squared. I FOIL this piece out. And then if I subtract 1 and square root both sides, I get that b is equal to the square root of 4x squared plus 4. I know I can drop the plus or minus because we're talking about the side length of a right triangle, so it has to be a positive value. Okay. So now what I have is cotangent theta, where I'm going to use theta down here. Cotangent is adjacent divided by opposite. So that's going to be square root 4x squared plus 4x over opposite, which is 1. And I guess I could probably simplify this a little bit more. Notice that underneath the square root, I have a greatest common factor of 4. So I can like break that at the multiplication symbol. Oops. And I could just write it as 2x squared plus x, or root x squared plus x. And I guess you could have done that simplifying at lots of different points. I just waited to the end, I guess, to do it because, I don't know, I didn't even know that I was going to need it. You know, maybe I won't need the square root 4x squared plus 4x. I mean, I'm just not going to wait till I got to worry about simplifying until I guess I got to simplify it. But you could have gotten after that whenever. Does that feel okay?
Yeah.
Good. Who's next? Happy to do more. Me, I thought I saw your hand up at one point. Okay. You're happy?
Yeah.
Sure. Natalie? Sheet 3. Okay, so this is one of these story problems. So you place a giant balloon in front of your friend's house. To ensure that it does not blow away, you tie 2 cables to the top of the balloon and secure them to the grounds on opposite sides of the balloon. The 2 cables are attached to the ground exactly 37 feet away. And one of them form a 55-degree angle with the ground, and the other is a 62-degree angle with the ground. We're interested in how tall is that balloon, right? So what I'm going to do is first I'm going to observe that the bases, or I have really kind of 2 right triangles in here, right? I have this one and this one. Everybody good with that? Note that the bases of these two right triangles aren't just half of 37. Why is that not true? Drake?
Different angle measures.
Yeah, since this is not an isosceles triangle, because the angle measures on the base angles are different, that height doesn't bisect the base. So I know that those are not the same lengths. So I'm just going to call one of them y, and the other one's going to be like 37 minus y. Because when you add those two up, you still get 37 for the whole thing, right? So I can then say in the green triangle that tan of 55 is equal to y, or h over y. And then in the other triangle, tan 62 is equal to h over 37 minus y. So far, so good. I'm going to multiply the first equation on both sides by y. Because to solve this thing, I have two variables in each of these. I'm going to have to solve a system. In the second equation, I'll multiply both sides by 37 minus y. And that just kind of gets rid of the fractions for me, which typically makes life a little bit easier to deal with. I notice that both of these equations are equal to h. So to solve them, I can just set them equal to each other. Along the way, I'm going to go ahead and distribute that tan 62. Notice when I make this substitution, I have only one variable left. I just have y's, which is great because now I can solve it. So I'll start by adding y, or putting the y's on both sides. So I'm going to add y times tan 62 to both sides. I notice on the left-hand side now, both of these have a greatest common factor of y in them. So I can factor that out. And then divide both sides by the quantity tan 55 plus tan 62. Now note on this that we're solving right now for y, which is not actually what we are asked for in the question. But I can use y to get h pretty quickly. And I know I'm still in degree mode, at least I'm pretty positive I am. I'm going to check real quick before I press enter. Yeah. Okay. And I know I need to be in degree mode because all the angles are described in degrees, right? So there's my value for y. To get h, I'm just going to use this equation. So h is y times tan 55. So I'm just going to take my answer and multiply it by tan 55 now. So my h should be about 3003. Nat, you cool? Okay. Amy, I saw your hand up earlier. Did you have something you wanted to ask about also?
Could you do letter E and
Page 3, letter E. Okay, so you're looking at this one. So we're going to start by going to the unit circle and evaluating what tan of 5 pi over 4 is. We're always going to start from the inside and work out. So going to the unit circle, I found 5 pi over 4 right here. I know tangent is y over x. So that's just 1. You good with that? Yeah. Okay. And I know that my range for arc cosine is 0 to pi. So then I'm going to go back to my unit circle, and I'm going to look for the place where the x coordinate is 1 between 0 and pi. Well, that happens right here at 0. That's the only place that it happens, between 0 and pi. So my answer is just 0. And then I'm done. Sure, no problem. Drake?
How do you get the range is like 0 to pi?
That's the definition. That's part of the definition. So that was something I have memorized. So again, in the very first day, we gave these fundamental ranges for the inverses. So unless it explicitly states that you're looking for an angle between some other measure, these are the ranges that you'd use for sine inverse, cosine inverse, or tan inverse, respectively. So we're using arc cosine, so we use 0 to pi. Is that okay?
Yep.
So again, those are 3 that you definitely want to make sure you're remembered, because we use those a fair bit. Who else? Happy to do more if there's more. Amy, is that a hand?
Yeah.
Let's hear it.
Page 4 for question number 7.
Page 4, number 7. Okay, so this is just pretty similar to the stuffed animal question we just looked at a moment ago. So it says we're standing somewhere and we look up and the angle of elevation is 43 degrees. And then we go 200 feet closer. And now it's 58 degrees. And we're looking for the height, right? So we'll just call this part Y. So I have 2 right triangles that I'm interested in. I have the big triangle, the yellow one, and then this little triangle, the green one. So for the yellow triangle, I can say that tan of 43 degrees is equal to opposite over adjacent. And then for the green triangle, I can say tan 58 is equal to opposite over adjacent. The first equation, I'll multiply both sides by 200 plus y. Second equation, I'll multiply both sides by just y. Oh my goodness. Now that I have them both equal to h, I can set them equal to each other. At the same time, I'm going to go ahead and do that distributing. So far, so good, AIM. Okay. I notice that I just have y's left. So to solve for y, I need to get them both on the same side. So I'm going to subtract y times tan 43 to both sides. After I do that, I notice that on the right side, everything has a factor of y in it. So I can factor that greatest common factor of y off. And then I can divide both sides by the quantity tan 58 minus tan 43. So 200 times tan 43 divided by tan 58 minus tan 43. That's going to give me my value for y, but that's not actually what I'm trying to solve for. Remember, I want h. If I go back, I can solve for h using that equation. So using my answer for y, I can just multiply that by tan 58. And bingo, bongo, boongo, there we go, 446.93. What you think? Sure. Do you think I'm going to put one of these systems problems on the story problems on the test? Yeah, that's a good bet. I definitely want to make sure I knew how to handle one of these if I were in your shoes. Eddie?
So could you show, you probably already did this, but could you show an example of using the unit circle to find the exact value of nested inverse function?
So that's just like what we did here on these ones.
That's like the ranges we gotta memorize.
Yeah. So you're just using the inside to either get the ratio that you're going to look up off the unit circle, or it might give you that you might have to use the inside to get the angle that you need to, but you know, it's the same. Ryan?
Are we gonna have to know like volumes for tests, like problems like 27, 28?
Yeah.
Like 27.
Sure. You take a jet ski from a cruise ship that is anchored at bay. You travel 60 knots at a bearing of 345 degrees for 40 minutes, and then turn to a bearing of 230 degrees and travel 55 knots for 30 minutes. From your position, how far away are you, and on what bearing is the cruise ship? Okay. So basically, we just have two legs of our journey, right? We leave, we go something, and then we turn and do something else. So I'm just going to think about this as two legs. The first leg of my journey, my bearing is 345. So we're over here. So 90, 180, 270, and then 75 more is going to get me to 345. So the standard position angle there, it's got to be 90 plus 15. And my distance there says we're traveling 60 knots for 40 minutes. So knots are nautical miles per hour. So I'm just going to do my knots times convert 40 minutes into an hour, or into hours, so divide it by 60. So that just gives me 40 nautical miles. Actually, let's write it underneath. So if when I break that into components, the x component is 40 times cosine 105, and the vertical component is 40 times sine 105. Do the same thing for the other one, bearing of 230. So we're over here. So 90, 180, and then 50 more gets me to 230. So in standard position, that's 90, 90, and 40, so 220. And my distance there is 55 knots times 30 over 60. So that's going to be 27.5 nautical miles. So the horizontal component is going to be that distance times cosine of my angle. And the y component is the distance times sine of that angle. So to get my final position then, I'm just going to be adding these together component-wise. What's up? Heard somebody start to say something. Okay. You can interrupt if you have a question.
How did you get like 40?
So the story problem told me we went for 40 minutes at 60 knots. So knots is nautical miles per hour. So to turn that into a distance, I have to multiply rate by time. But the time needs to be in hours. So 40 minutes over 60 minutes gives me my time in hours. And then I multiplied it by the knots.
Oh, so that's why it's 46. Okay, right.
Sure. We're good though? Okay. So calculator time, 40 cosine 105 plus 27.5 cosine 220. That's my x coordinate. And then the y coordinate is going to be the same thing, except I'm going to replace my cosines with sines. So I have negative 3142 and then 2096. Oops. Let me just double check that I copied that right. 2042, I wrote 92 and then 42, 96. Okay. So to get the final distance then, I just do the Pythagorean theorem on that, or really the distance formula, whatever way you want to think about it though, it's the same thing really. So square root of the x coordinate squared plus the y coordinate squared. So 37.77 nautical miles Still doing okay. And then the last thing I need is the bearing. To do that, I'm going to plot the point negative 37, 20.96. So that's going to be up here somewhere, right? So this is the bearing that I'm looking for. So 0, 90, 180, 270. And this is my alpha. So this bearing is going to be 270 plus alpha, since the last axis we passed was horizontal. Good on that. And the alpha is always going to be tan inverse of the absolute value, the y over the x. And now it's calculator time. So 270 plus tan inverse, absolute value, y over x. So 303.71 degrees. Ryan, are you okay? What I did there? Okay, Amy?
So when you're plotting,
Yep. Edmund.
So when finding alpha, it's always going to be y over x, right? But,
Yes. Yes. Because tangent is y over x. So whatever the point you just found by doing your addition or subtraction, depending on the context of the problem.
And then with the final, it's also dependent upon like the context of the problem. Like the lesson the other day, there's like one about weight.
Right. So depending on whether you're looking for where you add at the end or where you left at in the beginning would dictate whether you're being adding or subtracting, right? If you're looking for the end, then we're adding. If you're looking for the beginning, then you subtract, because it's like, okay, we know these things happen, but where did we start at? So it's like a subtraction problem.
But y over x doesn't change.
Does not change.
Regardless.
Correct. The numbers for x and y will change, but like that formula does not. Yep. Emily.
Like, what do you mean, like, subtract?
So here, there are problems where instead of adding the components, we subtract the components.
Oh.
On occasion, we saw one of those in the notes, I think. Let's look here real quick. Yeah, this was an example. So here, we know the initial and we know the final, and we're looking for this extra piece, one of the initial conditions. So like if you know what's happening at the end, you know you're going to have to be doing some kind of subtraction to find one of the beginning parts to it. If that makes any sense?
Yes.
Yeah, so what we did here was xf minus xi and yf minus yi. Is I used i's for initial and f for final. 1, 2, whatever. I felt like I was less likely to screw it up if I made sure I put f's and i's on it, because I knew that, this was f and I. And that all made sense. But you can name it whatever you want, taco and burrito if you want. Whatever the subscripts are. You can be creative. Or not creative. You can be super boring and, basic. I'm a basic guy. Basic's underrated. People like basic. Mia.
You do one of those problems with that subtraction. I think it's 29 problems. It's not that I did it wrong, so.
Well, let's,
Anyway.
yeah. Let's look here. So we can do that. And it says that so I think this is not a subtraction problem. I think this is just a regular.
I'm going to get you with the speed.
Sure. Okay. So that's just going to come from the distance formula. So here it says we're traveling on this bearing. Oh,
Because for this one, you find the speed in the bearing.
it's the same thing.
Okay.
Yeah, it's still, you're just using the Pythagorean. Hold on, let me read this one more time, make sure I understand what I'm reading. This is always the most challenging part of the story problem, is just making sure you understand what's being said. Can travel 460 miles per hour under its own power. If it travels on this bearing, and there's this much wind, is the plane's actual speed and bearing. Yeah, that to me reads as the initial is just just reads this to me as a standard addition problem. Since we don't know anything about like the end result, right? We're asking for the actual speed and bearing. I think that this is an addition problem, the way it reads to me.
Looking at it again, you're right.
Yeah. Like it's again, like sometimes just making sure you're really careful and read things and make sure we're understanding what's going on. I think that both 28 and 29 are addition problems from the read of things. To show you the subtraction problem example, here we're, like we've set this bearing initially, but we're told that actually, once we actually take off and start going, the bearing has changed because we're getting pushed by a wind. And the speed that we're expecting to go is actually, we're slowed down, we're at full power, but we're not going as fast as we should. Again, that's the result of some other force, in this case a wind resistance. So to find that wind, we're going to have to, I know the initial plus the wind must be giving me the result there, the final. So all I justify there is that to find the wind, I'm going to be doing the subtraction minus the initial, or the final, subtracting the final and the initial. So I do everything the exact same, right? I resolve everything the exact same into components. The only difference here is now when I do the wind, I do xf minus yf, or xf minus xi and yf minus yi. But that's the only difference. To get the distance, or get the speed, I just take the distance formula with the coordinates and do the bearing the exact same way. So there's no difference in the subtraction problem other than like instead of adding the components, we subtract them. But everything else is the same.
Thank you.
You just have to like catch in the problem that like, I'm supposed to be subtracting. That won't happen on the test. if that helps. So I'd expect to be adding on the test. Just FYI. Because we barely saw any subtraction problems, right? That seems like the least fair thing to do. Take the most obscure version of the problem that you didn't really practice a whole lot and like, oh, that's the one I'm going to test on. Right? Doesn't sound very fair. I try very hard to be like fair and representative. You know what I mean? We're not trying to trick you, other than when I'm telling you that I'm going to try to trick you, which is, I feel like, okay, because now it's like on the table that like, hey, I need to be careful about being tricked. You know what I mean? Like some problems are just like, this is a tricky problem and like, you need to know how to do this. But I'm going to tell you that I'm going to try to give you this tricky problem and try to fool you, which is okay now because it's not a surprise. But being surprised by getting tricked, that's rude. I try not to be rude. You know?
So is this you warning us there's gonna be like
No, but I'm just trying to justify. Yeah, but like I would tell you that like, hey, you know, like gonna have to be careful about this little thing, like this tricky thing can happen, and I guarantee you I'm gonna put this thing on the test. But it happened in like 6 problems in the 10 problems on the homework set. So like we did a lot of practice on this. We should be able to do this kind of thing. Like we did 1 subtraction problem in an example and like I think there's 1 in the worksheet. And that's it. That doesn't seem hardly fair to make that version of a problem the one that I would pick. That's what I'm trying to say. It's just kind of justify you that I'm not doing this willy-nilly trying to always pick the hardest things. But picking the representative things. And sometimes the hard representative is hard, right? And that's okay. But I'll tell you that we're going to do, anyways. I'm just rambling now. You guys happy with this? Emily? Yeah, so I actually have typed it up and it's already in the content library. So let's talk through this. So we have 2 questions where I ask you to use the calculator to find the value of the inverse. This is literally, you're just typing into your calculator what's on there, making sure you're in the right mode and writing down the number. You don't have to think about any more than that. Just to make sure you can actually use your calculator a little bit. 2 questions where you want to use the unit circle to find the exact value of the inverse. This is like the first page on the review. We did a couple, I think, out of there, right? You guys asked me about that or something similar to it. 2 questions using the unit circle to find the exact value of a nested inverse trig and trig function. So this was also something we looked at on the review. This was like these problems here, right, where you have an inverse inside of a trig function or a trig function inside of an inverse. One question where I ask you to find the algebraic expression for a nested trig function and inverse. This is like worksheet 4. Use the calculator to find the value of an inverse over a specific interval. That's like worksheet 2. 2 story problems. Of those story problems, what should you expect to see one of them as? The systems one, right? Where you have to solve the system with the 2 tangent equations. And then I have 1 navigation story problem in addition. That's your bearings. Cool. I broke the navigation story problem into some parts, so hopefully it gives you a little bit of direction as what to do if you get stuck. Like figure out the standard position angles for the bearings. Like find the final position, find the speed, find the final bearing or whatever. So it's like breaks it up a little bit so you don't forget to do something, gives you a little bit of narrative as to like what to do when. Yeah, just trying to be helpful. Emily. for this part? Would depend on the directions. The directions would tell you whether you wanted the answers in radians or degrees and how to round or whatever. As would, like, you know, the directions for like 2 and 3. Amy?
So, like what question? Did you say that was like worksheet 4?
Correct.
Oh.
Yep, worksheet 4. Okay. Everybody happy? Good idea what to expect? Alrighty then. I'm gonna